Spiral galaxies and no dark matter. Everybody is fascinated with the beauty of spiral galaxies with bright spiral arms. Their shape is very stable and lasts for billions of years and rotates very slowly compared to the stars rotating through the arms again and again. Milky Way, our home galaxy, is a spiral galaxy too, and our Sun and Earth are in Orion's spur of the Sagittarius arm at the moment, but will get out of the arm in a few million years. There is one long-standing problem. When astronomers, Vera Rubin especially, measured velocity of some stars near the perimeter of spiral galaxies, they found it was too high. Stars should have flown away from the galaxy if stars' trajectories were circular. To explain how these stars are retained in their galaxies, some scientists suggested that galaxy itself is in some ball-shaped cloud of dark matter, which provides additional gravitation pull to retain the stars. No such dark matter was measured or discovered so far. And when more data about stars' trajectories was collected, the theory collapsed. How stars move in spiral galaxies. You can find computer animations that were built of the measurements and see that stars move like a fish school, often changing direction and velocity, amazingly synchronous, and without collisions. Dark matter ball cannot do such schooling. It can drive stars in circular orbits only. You can say programmers got it all wrong. But in 2010 very precise measurements from our galaxy came, let me quote, phys.org, by an international team including several researchers from the Strasbourg Astronomical Observatory, near the Earth. Stars move towards the exterior of the galaxy at an average speed of around 10 kilometers per second, which is considerably faster than previously thought. The researchers were thus able to ascertain that the average speed of stars towards the exterior of the galaxy increases with their distance from the Sun in the direction of the galactic center, reaching 10 kilometers per second at a distance of 6,000 light-years from us, in other words, 19,000 light-years from the galactic center. Let me describe this observation in other words. While looking from Earth down into Milky Way center, astronomers noticed some stars rush from their low orbit to a higher orbit. That is known as Hohmann transfer orbit, when a satellite is given a thrust to get to a higher orbit. For such satellite to stay on a higher orbit, another thrust is required when the higher orbit reached. Otherwise, the satellite continues down by its elliptic orbit, fluctuating between two heights. And in reverse, if task is to lower a satellite from a higher circular orbit to a lower circular orbit, one thrust in the opposite to the movement direction first, then another thrust in the opposite to the movement direction when the lower orbit is touched. Without the second thrust, the satellite will continue by its elliptic orbit, oscillating between two heights. Later we'll see that for a star in a spiral galaxy, its velocity is boosted when the star exits a spiral arm, and its velocity is reduced when the star enters another spiral arm. Now we have to find what gives such thrust to the stars in spiral galaxies, and the value of it. Let's return to the Doppler redshift and time dilation. Let's look at simple imaginary task of calculating velocity of a ball falling of a moving platform. Now let's look at the same task when the reason for blue shift between two time zones is not because of Doppler effect, but because of time running differently in the white, at the left of the drawing below, and in the gray, at the right of the drawing below, zones. Let's say ZB blue shift observed by someone staying in the gray zone and looking to the white zone, and Z is redshift observed by someone staying at the white zone looking at the gray zone. Z and Z are related by Z apostrophe equals Z/1 plus Z, formula, so for small z. Z equals Z almost. From redshift perspective, this drawing is equivalent to the previous drawing. If two cases are the same from redshift perspective, then the impact on trajectories and velocities is the same. Why? Basically, it is known since Einstein's general theory of relativity, but was stated in other than redshift terms. It is because time changes cause geodesic changes of space, and light follows altered geodesic layout by taking new fastest path. Redshift, wavelength change, causes refraction by the same reason, light follows the fastest path. Change in geodesic layout impacts all object trajectories. In a sense, this observation is close to mass equivalency by Einstein, gravitational and inertial. The cause of gravity is not some force but in geodesy. So, we can just reuse math from the previous drawing, V equals V, ZC. And since Z equals Z, we get the following relation between velocities of the object when it crosses time zone border. V equals V plus ZC. The above formula is for non-relativistic velocities V and ZC, when redshift Z is close to 0. For relativistic velocities, we are to use another formula that I put at the end of this chapter, and add velocities using Einstein's formula for velocity addition. Coming back to the spiral galaxy problem, the solution is in time zones. Time in spiral arms runs faster than outside the arms, in gray areas. Or time in gray areas is slower than in spiral arms. Here are several facts confirming time difference between arms and non-arms. 1. Arms are brighter, because time runs faster, stars burn faster, highlighting the area of the faster time. 2. White and blue stars are more common in the arms and yellow and reddish stars are more common in the gray area. It is because not arm areas are blue-shifted, red-shifted to each other. 3. There is an impression that new stars being born when entering the arms, and an impression that some stars die when leaving the arms. The actual reason is different, and it is good to discuss it here. Some stars of spiral galaxies are on the edge of a critical mass, their burner is either flickering, or goes on and off. By now we understand when time speeds up, the probability of certain events goes up, in this case, the probability of hydrogen atom collisions in a star that ignites a star that was off, and was on the edge of a critical mass, when such star enters an arm where time runs faster. And when such star exits an arm, its burner goes off again, so for an external observer, star dies on exiting the arm. And even more. Why stars move in a fish school manner we already explained using Hohmann transfer orbit and by the formula. V equals V plus ZC. Velocity boost happens when star exits an arm, enters a gray area, and velocity is reduced by ZC when star enters an arm. Why stars do not collide on such maneuver? 2 reasons for this. All stars' velocities change by the same value, ZC, and they try to follow changed geodesic lines. Another reason, and it was recently confirmed for the stars at the center of Milky Way, stars are saved from the collisions by their magnetic field pushing them away when they come close. They are repelled like the same polarity's magnets when coming close to each other. See screenshots from a video posted on YouTube that shows 2 stars on the collision course and how they bounce off each other. And now coming back to Vera Rubin's paradox, when she plotted observed maximum velocities of stars by distance from the center of a galaxy, she received velocities like that. Vera Rubin's delta plus const a-0 middle.5 plus fluctuations. Apart from const a-0 middle.5 that comes from the gravitational pull, the rest we already figured out in this chapter. Middle dot fluctuations come from Hohmann transfer orbit and non-circular orbits. Middle dot the puzzling constant Vera Rubin's delta is ZC, constant of the boost. From Vera Rubin's delta of a specific spiral galaxy, we can find redshift between arms and gray areas of this galaxy. Z equals Vera Rubin's delta, C. Please take a moment to appreciate that a small redshift 1/c has a profound effect on the galactic processes. It switches stars on and off and messes up all orbits. Vera Rubin measured velocity at the perimeter of 5 dozen galaxies. Results were at 100 to 300 km per second range, half of them around 300 km per second. That gives Z around 0.001. What a big impact should be anticipated for larger redshift values. Meaning, what a profound effect should be anticipated when time differences are big. When we were calculating the boost value S, we rounded formula. 1 plus Z equals 1 plus S/C0 middle dot 5. 1S/C0 middle dot 5. For small values of redshift Z, let's do exact calculations for Z0. 1 plus Z. What happened 65 million years ago? From nationalgeographic.com. Ask someone how the dinosaurs died, and chances are they will tell you about an apocalyptically bad day 66 million years ago, when a huge asteroid slammed into Earth and triggered a nuclear winter. This event left behind distinct traces in the geologic record, as well as a vast crater off Mexico's Yucatan Peninsula called Chicxulub. But since the 1980s, researchers have debated whether volcanoes in ancient India may have been an accessory to the mass extinction, or even its main driver. According to the two teams, the massive volcanoes, called the Deccan Traps, started erupting about 400,000 years before the Chicxulub impact and wrapped up about 600,000 years after the end of the Cretaceous period. At least half of the volcano's total erupted lava spilled out after the impact. The eruptions could have injected massive amounts of greenhouse gases and particles into the atmosphere, changing Earth's climate in ways that stressed out late Cretaceous life. Then, in a 1-2 punch, the impact's nuclear winter would have sharply cooled Earth and caused ecosystems to collapse. After such a good explanation would be strange to ask, but why this happened and why 65 million years ago? This strange question has a very precise answer that brings some adjustments to the explanation above. Let's start from the Wikipedia's map of Milky Way and our solar system in it. Actually, it is incorrect that our Sun has a circular orbit in the galaxy. We have learned that stars lose velocity when they enter an arm and gain velocity on exiting an arm. Let me try plotting approximate Sun latest orbit with the red line below, near the yellow circle that is a good approximation for the latest 65 years. Sun Sun's circular orbit is estimated to have 225 250 years period. Earthsky.org. We go with more than 250 estimate, considering that real orbit is actually longer than the circular. That gives us a point when Sun left Scutum Centaurus arm, either by the yellow circular orbit or by the red combination of elliptic orbits, approximately 65 years ago on the map above. Let's see how leaving an arm can cause tectonic and volcanic activities and asteroid events on Earth, and the decline in solar activity. When solar system left the arm, it entered slower time zone. Fusion processes and solar activity slowed down because hydrogen atoms slowed down their run. Despite fusion, in Sun, and fission, in Earth, chain reactions slowing down due to the time dilation for atom or neutron runs, there is no impact on radioactive decay for a single atom, because internal time of an atom is not impacted. There are estimates that half of contribution to the Earth tectonic and volcanic activities come from the decay of radiogenic atoms in the Earth. Nature.com, the CAM-LAND collaboration reported that heat from radioactive decay of radiogenic isotopes such as 238U and 232 contributes about half, 21 TW, of Earth's total heat flux, 44.2 plus minus 1.0 TW, and that Earth's primordial heat supply has not yet been exhausted. Blogs.scientificamerican.com. Earth is chock full of such radioactive elements, primarily uranium, thorium and potassium. Over the billions of years of Earth's existence, the radioactive isotopes have been splitting, releasing energy. That energy heats the surrounding rock and keeps the elemental forces of plate tectonics in motion. Now imagine what happens when time on Earth slows down, but the energy flow from radioactive elements decay stays same. Or, if time on Earth slowing down is hard to imagine, then let's imagine relatively the same scenario: time on Earth stays same, but energy flow from radioactive decay increases. Either way it leads to the tectonic activities and volcanic eruptions. That explains how CO2 production increased due to the volcanic activities, and how photosynthesis by plants consuming CO2 and producing oxygen decreased due to the solar activity decline. That was the leading cause for big animals' extinction. Asteroids did not help either. Why asteroids are more likely to collide with Earth on exiting or entering an arm. We discussed a similar question in the chapter about spiral galaxies. Objects' trajectories change on entering or exiting an arm. Stars rotating in the same plane avoid collisions by repelling each other by same polarity magnetic fields. But Earth has no such protection, its magnetic field is not that strong and asteroids have none.